Okay, I think we are fine. So let's start the webinar. So hello everybody. This is Luboš Pirkl and Radek Máca from CFD Support. Welcome to the webinar on Turbo Machinery CFD, which is a smart, easy, and affordable CFD software for rotating machinery. I hope everything works well. Anyway, in case of any technical problems, feel free to contact us in the future, and we will gladly answer all your questions and comments. The webinar is going to take about 1 hour, depending on the number of your questions and reminders. The webinar is being recorded, so the recording will be made available on our YouTube channel. The topic of today's webinar is an axial fan. So I think we're ready. So I think we can get to the action. So yeah, here is the presentation. So let's start. So let me start with who we are. So please let me introduce us a little bit. So this is me. My name is Luboš Pirkl. I'm co-founder and managing director of CFD Support. And today I am sitting here with my colleague, Radek Máca. Hello, Radek.
Hello, Luboš, and hello everyone who is watching.
Hi. So how are you today?
Yeah, I'm very fine. And how are you today? And how's your CFD going?
Yeah, I'm fine, thank you. So I guess we all are ready. I only know that Radek is our head engineer and senior developer here at CFD Support, and he will take care of the technical part of today's webinar, and I guess he's gonna show us really big things. Okay, so yeah, I think it's time to switch the camera off for a while. We'll get back later in this webinar. And okay, and yeah, so this is Radek in the presentation. Yeah, hi Radek. Okay, hi again. And okay, the webinar is going to take about 1 hour, depending on number of your questions and comments. There will be 3 parts in this webinar. In the first part, I will give a general introduction of Turbo Machinery CFD. I'm gonna go for the main points, for the benefits and features of Turbo Machinery CFD. In the second part, there will be a live example where Radek is going to show you how to simulate the axial fan in Turbo Machinery CFD. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. Feel free to put your questions to the special window, and we will answer them later in the webinar. Especially in the beginning of the webinar, we are going to be quite general, but feel free to put your questions, ask about any detail, and we will gladly answer it in the Q&A session. And you can put very detailed questions, and we are here for you, and we will do our best to answer the best. Yeah, so I'm gonna say a little bit about CFD Support. So CFD Support company is a private engineering company dealing with computational fluid dynamics. In general, we are used to deliver complete CFD engineering projects all across the field. We do quite a lot of outsourcing work. Then we deliver extensive OpenFOAM training and consultancy, as well as OpenFOAM support and custom code development. And of course, finally, our flagship product is Turbo Machinery CFD. We are now rebranding Turbo Machinery CFD to TCFD. So TCFD stands for Turbo Machinery CFD. Yeah, which brings me to Turbo Machinery CFD. So let me give a brief description. What is Turbo Machinery CFD? So Turbo Machinery CFD is a unique software based on OpenFOAM, and it was designed for simulations of all rotating machinery, such as pumps, fans, compressors, turbines, turbochargers, hydro turbines, etc. It was designed both for radial and axial machines, both for incompressible and compressible fluid flows. The workflow is comprehensive, so it's complete. It's a complete workflow. that covers all the engineering steps, from the pre-processing over the simulation run to the very detailed post-processing of the results. Turbo Machine CFD is fully automated. It's independent on any other software, and on the other hand, it's fully compatible with any other software. And the thing is that the user simply puts the data in. Turbo Machine CFD does its job, write the results report, and the user finally reads the results report, and that's it. So Turbo Machine CFD can be used as a black box and also as a full sophisticated CFD code at the same time. So all the options are open. So the beauty of Turbo Machine CFD is it's the user who decides how deep to dive into the problem of CFD. So it's absolutely on the user how many details to consider and what to do. So it works as a black box and as a sophisticated full CFD code at the same time. We believe that Turbo Machine CFD is unique, at least for 4 reasons. So number one would be Turbo Machine CFD has no licensing policy, which means our clients can keep Turbo Machine CFD forever and they can use it for unlimited number of users, jobs, or cores. This gives the investment in Turbo Machine CFD a permanent value. And also this means our clients can scale their CFD simulations in a really big way. Number two would be Turbo Machine CFD is fully automated, which means all the workflow from the initial data to the final results report, it can be run by a single click or a single command. And for this reason, Turbo Machine CFD is extremely effective. Number three would be we deliver the extraordinary technical support. We keep custom approach to every customer, to every issue. We never leave behind any of our clients or users, and we are very flexible. We support our clients even in matters out of the turbo machinery field, for example, in numerical mathematics, physics, CFD, IT, or even software engineering. And the last one would be the real tutorials are included in turbo machinery CFD, so the user they have no doubts about the best practice settings because they can see the best practice settings for each major kind of rotating machine in the tutorial. So the start of using turbo machinery CFD is very smooth and quite very easy, I would say. There are many other benefits of using turbo machinery CFD. I'm not gonna go for all of them. We can discuss them, for example, in the Q&A session. Yes, there are some technical details I would like to mention. This is quite a technical slide. I'll go quickly through it. So Turbo Machine CFD is available both for Linux and Windows operation system. There's graphical interface based on ParaView, so 100% of workflow is based on graphical interface. So it's very user-friendly for this reason. The trial version, the demo version is available, so anybody can try Turbo Machine CFD for 1 month, and after that he or she can decide whether to go ahead with us or not. So it's very transparent. The real tutorials are included. The HTML web responsive reporting of the results during the runtime is available, so all the results are ready to be seen anytime. Yeah, there is a special set of plugins for ParaView to enable turbo machinery post-processing of all the rotating machines. The workflow is scriptable in Python. The documentation and manuals and videos are available. The resources are available online, and what's the most important, our development is user-driven, so our users can ask us what feature to develop in the next version, and we are very, very sensitive on this, and we really deliver what's requested from our users. So users-driven development. Okay, now this is Radek's time, I guess. So it's time for a live example where Radek is going to show us how to simulate an axial fan in Turbo Machine CFD. So it's going to be a real live example. So I switch the presentation to Radek now, and here you go, Radek. So It's your turn.
Okay, thank you, Bosch. Thank you, Bosch, for a nice introduction for me. So a lot of information was said, so I will directly start with the technical part. So first of all, I should introduce today's geometry. So for all of you who would like to try it by yourself, you can ask us for the demo version of the turbo machinery. So you will get the demo, and you can try, for example, today's webinars or all the workflow we are going to do today. You can do it by yourself. So you can ask us for the demo version, and inside the download section, you can download today's case, which is this Axial fan. So just simply click, and here you fill this form, and you can then download this case for Axial fan. Well, to tell more details about the geometry, it was generated by CF Turbo software. So we are in a close cooperation with CF Turbo company, which is developing this designing software to design almost any type of turbo machinery machines. And today's webinar is basically this Axial fan geometry. So this is the default case inside the CF Turbo. So here you can design your geometry, and afterwards easily export it to TCFD, to the turbo machinery CFD software. So that you simply export it, and then if I go to my disk where I save this geometry, which is in my OpenFOAM installation. So I am using the latest version of TCFD 17.10, and here are my home folder, and here I created webinar folder for today's webinar, and these are our today's geometry. So there are two, because you have the option to simulate a full wheel, which is let's say not so convenient for full wheel, because we have also the option just to simulate a segment of a full fan geometry, and save a lot of cells and a lot of computational time to get the results for the Axial fan. So from the export, or what you need at the beginning, is the input geometry. We provide, or our software provides, both the STL geometry, so this is the usual export for almost any CAD software and design tools, and the configuration file, which is not compulsory, but you can preset the TCFD file, and then you can directly run the simulation without, let's say, any setup. So at the beginning, you need the geometry. So for today's webinar, we will have just the CAD geometry, or the geometry in the STL format, and using this input, we will do the whole workflow from defining the computational mesh to really evaluating the results. So you can simply watch with the STL. You can open it in ParaView, and you can see each part of the geometry. So for example, this is the half of the rotor part. So here I open the two types of the geometry. So first, you can, as I said, you can work with the full wheel geometry, as it is rotor part, stator part, or you can just cut off one segment, which is periodic, and use this geometry, define the computational mesh for this geometry, and simulate CFD process. So basically, I can, for example, this is really only one segment from the stator part and the rotor part. Okay, so this is the geometry we are going to work with. Okay, this I can close. So to start, as I said, you can use preset TCFD file. So it basically contains all necessary parameters which has to be defined for a successful run of the simulation. Basically, there are description of the fluid type, of the how many processor you would like to use, and many others. Or you can start from scratch, as I will do, because you will see the complete workflow to set your geometry or your CFD simulation from scratch. So to do so, after the installation, you will have this TCFD icon. So I will simply open it, and it opens directly the graphical user interface, which is implemented inside the ParaView, because the ParaView itself has a lot of features and nice tools for CFD visualization and processing the scientific data in general. So if you run the TCFD, then you here in the pipeline browser, you will see the TCFD source, basically which holds the settings of the simulation and which holds these menus using which you can set the CFD simulation. And also the components part, which is really the geometry, which is the geometry of your machine. So you can also about that. Okay, so these two options are implicitly loaded. So inside the settings part, in this menu, we are going to set up our geometry. So first of all, we would like to set the file in which our setup will be stored. So I will click just save, and I will find my working directory. So I will go to my Matza directory. Here's today's webinar, and I'm going to set up the Axial fun segment because it is a little bit more complicated than the full view, because we have to set these periodic boundaries. Okay, and I will create here, for example, my case file in which all my setup will be stored. Yeah, anytime you will click on apply, it will show you what is not filled yet and what needs to be filled during the setuping process. So you can see here that something is missing in the efficiency probe. So we will see later on what is needed to set up. So I can close it for now. Okay, so first of all, the setup file was set, and now we have to choose the machine type, because the software provides many basic types of the machines. So for today's we have fan. Inside the simulation menu, we have to set up time management, so we can set steady state simulation or the transient. So for today's we will use the steady state. Number of processor, so I will change it to 4 because my laptop has just 4 cores, but there is no limitation to use any number of cores. So if you have really high performance cluster, so you can use 100 cores without any restriction. Numerical order of the simulation, so for this example, I will use the first order scheme. This convergence check, if you enable it, then during the simulation, the simulation is always watched, and if the criteria which tells if within the last 100 iterations the efficiency, the flow rates are stable, so are stable means the difference is less than 0.1%, then the simulation is stopped before the maximum iteration is reached. So you can save some time if you enable this option. Well, so we can go on inside physics. Here you can define the fluid properties. So in my case, I will use the air, of course, because there's axial fan with the slow flow rate or with the low flow rate and with the slow speed, so we can simulate it as incompressible case, which is an usual option. And here I can set the parameters of the fluid, so dynamic viscosity, reference density, reference pressure, so it means usually it is a pressure at the outlet or at the inlet. Of course, reference temperature and heat capacity ratio. Okay, so this is the setup of the fluid. Of course, you can use different variables. If you are more if you are friend with, for example, torr or psi variables, so you can also set in these values. Okay, so this was the physics, and now let's say the most important part, let's say, of the CFD simulation setup is to define the mesh, the computational mesh. All right. Okay. So we have two options. So we can define the geometry using the STL files, and then the computational mesh is created automatically using our setup we defined here. Or also we can use an external OpenFlow mesh. It means you can use, for example, MSH mesh format, which can be using OpenFlow utility converted inside into the OpenFlow format, and this type of mesh can be loaded directly here. But for today's webinar, we will use these STL files. Okay, to start from the very beginning, the scale factor means in which dimensions the input geometry is. So, for example, my geometry is in millimeters, so I have to tell that my input geometry is in millimeters. I have to know, because the solver needs to know how to convert the dimension into meters, because implicitly the solvers uses meters. So origin is the point of the axis, and axis of the rotation now points to the z direction, which is also our case. Feature edges, it's some angle which can generate so-called feature edges, which are the objects which can help the measure engine to follow the sharp edges in the input geometry, and it will also appear in the final computational mesh. Well, number of components. So whole geometry consists of several components, which follows its physical shape, let's say. So usually it is split into stator parts and rotor parts, which are then connected together to create a full geometry. So today we have two components, rotor part and stator part. Okay, so now you can see that we have to define two components. So I will start with the first one. So I will say which type of mesh I would like to create, or which input I would like to use. So directory with STL files. It's our case for today. So I will go again to my working directory, where I defined, or where I exported my geometry, the STL format. So it is here. So here are the STL parts of my geometry. So I will click on OK. Then it will automatically appear in this menu, as you can see. So first, I can define a component name. So I will start with the rotor part. So the name is rotor. Number of periodic segments, because I'm using the segment, not the full wheel. I have to tell how many blades builds the full wheel. So in my case, it is 20 blades. And now I have to assign to each STL the type of the boundary, which will define my boundaries in the final mesh. So impeller blades, there are several types which are very straightforward and follows the physical type of each part of the geometry. So impeller blades, I should set as a blade type, impeller hub as a hub, impeller inflow. there are two types of inflow. Let's say there is an inlet type and the inlet interface. So for really physical inlet or the physical outlet, so maybe it's really the input, the entrance to my machine and the exit from my machine, you have to be set as inlet. So this is really physical inlet into the domain. And for outflow, because my rotor will be connected to the stator part, I have to use the outlet interface. Yeah, so interface really means the interfaces. Now I have to distinguish if it's outlet or inlet. So outflow will be outlet interface. Impeller periodic A and periodic B. So these are the periodic sides of my geometry. So I think I can, anytime you assign something and you enable this I next to the component, so the geometry will appear. So yeah, another warning that something is missing. So you can watch it always and fill these parameters. So this is what I set until now. Yeah, so now nicely I can see the geometry. And now I will add the impeller periodic. So there is special type rotational AMI because it is rotational symmetry between these two periodic parts. So rotation AMI. Again, if I click on apply, yeah, warning is. But still I can see what I have added, right? And so I will finish this part. So rotational AMI for the periodic A and B. Oh, not translational, but rotational, of course. And by the right click, I have to assign, I make a couple, yeah, to know what is the neighbor of the periodic B and vice versa. So by clicking on one of these items with rotation AMI, so I do a right click and automatically there is only one option. And now I can see the connection which is colored in different color. And the impeller shroud, there is a type shroud, right? Okay, so this is my full view geometry. And this is just there's the segment part, and now you can see that all is defined. And of course, the outlet interface has the neighbor component 2, which I am going to define in a few moments. So I will connect it directly to component 2. If you go a little bit lower, now you can see the topology graph, which helps you to define your geometry and to see how your geometry is defined, right? So I have rotor, the inlet is this name of the STL, and here's the outlet. And something is connected to component 2, which is not yet defined. Okay, so now you can see that there is a several column. So here's the type which we have used now, and the rotor column which defines which part will be rotating. So I have to check the plate is rotating, how it's rotating, and also the shroud, because it's a shrouded case, so also the shroud is rotating. Here are the minimum and maximum refinement. It tells you how fine the mesh at these boundaries will be for the final mesh. So we suggest to use the default values at the beginning. You can define the bounded layers by just adding the number. Okay, so now it adds 3 layers at the blade. So I will leave it at 0 to be the whole process quick for this particular case. And the mixing plane, number of mixing planes, which is basically the treatment, how to connect the interfaces between rotor part and stator part. So usually, for example, default number is 10 for this axial type, axial machine of this type. Okay, there are another window to be set is the background mesh size. So usually let's say the magic number is is to set this number, set this background mesh size to the if you take the diameter of the wheel and you divide it by the number 75, you obtain this magic number, which is really nice to it's really okay for, or you can always get a nice mesh for this setup. So I think the wheel has about 300 millimeters. So if I divide it by 75 roughly, so I will get something like, let's say, 4 millimeters. Then I have to choose the internal point. So I have to say the meshing to the meshing software, which if it should mesh the outside or the inside of the geometry. So if I visualize the point, it will appear in this render view, and I have to put it inside. Okay, so if I rotate it, and now we can see that it disappears inside. So I think this is okay. So now it automatically sets its internal point. Wheel diameter. I think it is important for some fun characteristics which need this constant of the wheel diameter to compute. I think that is psi variable or psi parameter. And other parts are not important in this case, so I will omit it. I will leave it as 0. And yeah, this is all what I have to set. So now I do the same for the component 2. So again, I will load the STL directory, the same directory because the stator part is in the same directory. The component name I define as stator. The stator part has I think 15 segments. And then now I have to assign the type. So So impeller plates, I need to now define this stator parts, which is this band gate names. So band gate plates is type of it's blade. So I define the type blade. Hub is a hub. Inflow, because it is the interface, is the neighbor of the rotor outflow. So I have to define it as inlet interface. Outflow is just the outlet, because the physical outlet from my machine. And periodics parts I have to define as rotation AMI. So I'm going to do that. So now I have to make a couple, and of course, if I go to my topology graph, you can see that there is no connection, there is no solid arrow between the rotor and stator. It is because I didn't connect the inlet interface to the component 1. So if I do that, so now you can see that my topology graph looks nice. Everything is solid. So it points you that everything is defined correctly. And last part, I have to define this shroud part, which is here. Okay. Okay. Okay, so I can read here, but there is no rotating component, so I forget to check the component 1, which is rotor, that should be rotated, which is here the options. Yeah, just that the rotor is rotating, of course. So I have to check it here. Now, no warning message is shown, so it's good for me. Okay, so this was the rotor part and the stator part. So I have to finish by defining again the background mesh size. So I will click. I will define the background mesh size, which is the same as for rotor part. Now inside the components part, you can see the stator part appears, and here, if I use this VTK block colors, then it will nicely corresponds to my topology graph. Okay, so last point is to define the internal point for the stator part. So I will go here, and I will put inside. Okay, nice. That is all for the mesh setup. Okay, so we can go on. So next menu is the speed lines. Here we define the computed points. So how many points, how many different conditions we would like to simulate within one simulation. So we can define several speed lines, which is useful, for example, for compressors, maybe also for fans if you would like to generate full map of the fan or of the compressor. So in this case, I will use just the one speed line. You have to define the rotation speed, of course, which is 4,500 for this axial fan. You have to be careful which direction to set, because it follows the right-hand rule. So if your thumb points the axis of rotation, then your finger shows you which is the positive direction of the rotation. So this is the positive. And if you see, the axial fan is designed to rotate in the opposite way, anti-clockwise direction. So I have to define it as a negative value. Then I can, for one speed line, I can have several simulation points with different pressure drops or with different volumetric flow rates, for example. So, for example, I will set 3 points to be simulated. This is the maximum number of iterations for one point. So, I think for this case, 500 is enough. Then I can set the turbulence model. I have several options. So, I will use the K-SST. I can also define some roughness of the wall. So, this is not the case. Inside the inlet boundary condition, here I have to define the boundary condition for each point. So I will use the volumetric flow rate at the inlet. I think the design point is something about 3 cubic meters per second. So I will set, for example, some range between along this point. So 2, 3, and 4. Usually, it is useful to start with the highest flow rate, because it is simple for the solver, or the solver converged more smooth for high volumetric flow rates, and for low pressure drops, for low pressure ratios, of course. Then inlet turbulent energy intensity and dissipation rate. So I use these defaults, which are convenient for this axial fan. At the outlet, we will simply set the fixed pressure boundary condition. Here is the 0, because this is the relative pressure, because as you remember in the physics, here we set the reference pressure, so then we use here the relative pressure, so which is 0, so basically the ambient pressure for my setup. Then the initial gas, of course, so the pressure is 0 because it's relative pressure, and the velocity should point the flow direction, and I will set, for instance, something like 10 meters per second, because I know that this is a sensible choice for my axial fan, because I know its parameters. And again, I will set it as default, this turbulent energy and turbulent dissipation rate, because these are just initial conditions. Well, inside the simulation controls, I can process, or I can change some advanced parameters, which is the under-relaxation factors of the solver, and some bounding limits, which may help, help the solver to start the simulation without any problem. The post-processing part, here I can define the averaging window. So again, the 100 is optimal value for this type of Axial. So using this window, all variables are averaged to have the average solution at the end, and all variables are averaged using these windows. Using this window, you can also change the units which will appear in the report. So again, you can choose, for example, PSI if you want, and etc. Then there are efficiency probes. So the default option is that all, for example, pressure drop, efficiency, and other variables are evaluated from the inlet and from the outlet. But for example, you can also define just that you want to see the efficiency of just of the rotor part. So you can easily add the efficiency probe. You can define the inlet patches to be used for evaluation. So just the impeller and the torque patches. So usually everything what is rotating. And the outflow will be not the outflow from the stator, but from the rotor part to have the efficiency only at the rotor part. You can use it to watch the convergence using these efficiency probes, both or only the one you can choose here, and you can distinguish if you would like to use the average using the flux weighted averages or just the area average. So, for example, this is the area average option, and this is the flux average option. Then you can apply the blade-to-blade views, which will be automatically generated after the simulation is finished. So these are the default values. So you define basically which part of the mesh is used, usually the rotor part, what is the hub, what is the shroud, which fields you would like to visualize, and which span to use. So basically it is a relative coordinate for the radial slice between the hub and shroud. So this is the slice directly in the middle between hub and shroud. And meridional average. So it makes a meridional average and visualize the field you define here. You can also add the graphs from your previous simulation, for example, to compare the simulation. Here are the advanced meshing options. It uses the SnappyHex mesh, so you can, for more advanced users, you can change something here, but everything is preset with the best practice option, I would say. And the scripting, you can add the Python script, which may include any of your, I don't know, utility or feature, or if you have the special requirements for evaluating something or setting something, so it can be done using this scripting window. Okay, so this is the setup. So after I am satisfied with the setup, so I will go back to the general. I will save my current setup to keep it for further simulation, for example. And when I am done, so I will click on the settings, and now this TCFD manager appears. So I will click on it. Now I see here the new window using which I'm able to manage the simulation. So first of all, I have to define the case in which my simulation will be stored. So for example, my simulation. Usually it should contain some information of your setup if you are comparing more simulation with different conditions and so on. Then I have to click on write case. So basically it creates all the necessary stuff for the CFD simulation. And after that, I can simply run all, which do the whole process automatically. So if I click on run all, it creates the mesh automatically. It runs the simulation and creates the reports. Or you can go step by step. Yeah, you can first build the mesh for each component. Then you can check it, you can show it directly here, and watch it if you are satisfied with this mesh, and then go on for the simulation. So first, I will just click to the mesh all option. So now you can see the progress. Yeah, the component 1 is now yellow. You can see the time of the meshing now. So it creates the mesh. So now we can see that the mesh for the rotor part is created. Now the mesh for the stator part is creating, and after that the final mesh is created, and this mesh can be used for the simulation. So if we wait just a few seconds, okay, now the mesh is done. Anytime I can watch the mesh. If I click the show button, then I click on apply, and I hide. Yeah, I have to click on this render view. I will hide this component part, and this is my final mesh. Okay, so this is the computational mesh. And now I can simply click the run calculation, which runs the calculation. Of course, you have always the information which point is computed. So we have set 3 points, how many iterations it takes to get the result for the first point, how many iteration is already done, and the time left for this point. And of course, here are the information about the overall simulation. So the total number of iterations for all points and the time left. So we can see that it will take probably 5 minutes. Of course, you can anytime skip to the next point. You can anytime abort the calculation. And what is important, you can click, and anytime you can generate a report. There is a light report which is generated fastly and can be, and usually it is designed to be run during the simulation. So it creates the basic information about the simulation, like the actual residuals of your computation and actual efficiency, and maybe there's torque which is evaluated at the point you click on this light report. So here's the progress of the report generation, and after that it is done. After that, you can see the report directly here in this HTML window. Yeah, so you can nicely see here. You will get the information how the simulation is set up, the current flow rate, the current residuals, the current efficiency, convergence. So this is the light report. And at the end, or if you were like click just to run all, then after the end of the simulation, the full report is created. And for example, I have run the simulation before the webinar started, so I should have the results here. So Axial fan segments. So this is the case when I run it. This is my webinar case, which I named as it is, and this is the case in which you can again load it inside the TCFD file, or if you would like just to watch the HTML report, it is automatically generated in the report minus the name of your case, and it can be anytime open in your HTML viewer, and you can see the results anytime after the simulation. So you can see nicely the geometry. You can see the basic information about the simulation and about the mesh, how big your mesh is, the details about the mesh, the quality of the mesh, of course, Y-class value at each part of the wall. So it's important for turbulence modeling. How long does it take to get the results? How many processor was used? And many others. Residuals along the whole simulation. Here are the fan characteristics. So this is so-called flow number and compression number. So this is the nice graph of it. Of course, efficiency. So here for this simulation I defined more points to get really nice and smooth efficiency graph. You can watch the convergence process. You have the information about the torque, of course, again in the you have the information as a graph, or of course as a table of values. Total pressure difference between inlet and outlet, or between what you define, for example, only at the rotor if you define it, or the pressure difference along the whole machine and whole geometry. Total pressure per interfaces. So for each simulated point, you can see the pressure at each interface. So for example, this is a stator outlet, so you can see the pressure at the stator outlet or between the stator and rotor part. So it's interactive also, this HTML. The same holds for the residuals. This is so-called total pressure profile, so you can see the profile along geometry, how the pressure drop is made at each part of the geometry, of course. Velocity magnitude per interface, so again you can see the velocity magnitude at each interface for each point. Also the convergence process. Circumferential and meridional angle, so we can check the attack of angle between, for example, the impeller or between the stator part. So you can read it here nicely. And here are the parts of the automatical visualization. So here's the blade-to-blade view. So I will set, for example, setup one, which is the streamlines at the radial slice between half-inch route for the span 0.1. So it is, let's say, the relative coordinate is 0.1. So it is close to the half part. And you can see for each simulated point, you can see the flow rates. You can see the streamlines visualization with the velocity magnitude. You can really watch the details about the flow. So you can see here for the last point there's some recirculation occurs behind the trailing edge, and so on. So you can also make this analysis using these images, which is automatically generated. The same for another span, and so on. And of course, meridional average, so it is the average along the wheel of the static pressure. So we can see the static pressure distribution at the slice which goes through the axis of rotation. Okay, so this is the automatically generated report. So it contains all important information about your simulation. You can compare it with your old simulation or with the new simulation. You can compare it with another type of the geometry. So if you, for example, make the optimization, which nicely can be done using the configuration file, because you only change few lines, and you can run the simulation again with a different geometry with the same setup. For example, I created the same case with the same setup with the full wheel geometry. So I will go, which is my computed case webinar. Somewhere here is my report. So this is the same simulation with the full wheel geometry. So for example, I need to have almost more than 3 million cells to get the similar mesh as for the segment case, but still this mesh is a little bit rough. And because there is option to add the old or different graphs, so here is, for example, the comparison of the simulation of the same geometry of the same machine with the segment part. So this is the results just for the one stator blade and one rotor blade, and the green one, the green one is for this one blade geometry, and and the violet one is for the full geometry. And in this case, you can compare a lot of results with different shape of the blades and so on and so on. And always you get this report automatically. Okay, maybe my time is almost up. And also, anytime you can see the results. Okay, the simulation is done. So anytime you can click here to show results. You can click on apply. So you can also make your own visualization. So this is, for example, the static pressure distribution for each point of the simulation. So you can make your own visualization and analysis. Okay, so my time is up. So thank you for the attention, and I have to hand the presentation back to Lubos. So Lubos, can I?
Of course.
Yeah, perfect.
Of course you can.
I will do it now.
Okay. Okay. So thank you, Radek, for your remarkable example. So I will quickly finish my presentation. So yeah, perhaps before I do that, I will ask everybody who has a question to put a question. We will gladly answer it. So just take your chance. It's your time. And I'm going to finish with how to get turbo machinery CFD. So the trial version, the demo version is the full version for 30 days. So anybody can get this to try it and decide afterwards whether to go ahead with us or not. So it's very transparent. Whether you like it, you can have it. If you don't like it, it's not a problem. Our business model with turbo machinery CFD is very different from standard commercial codes. Turbo machinery CFD is always perpetual, and our users, our clients, they can keep turbo machinery CFD forever and use it for unlimited number of users, jobs, or cores. And what is paid for is the first delivery and the later technical support, updates, and maintenance. So for this reason, it's very different from what is available in the market. And we believe it's pretty unique and pretty useful this way. We believe turbo machinery CFD is very affordable. So last year we decided to fight hard for the universities. We have special program for the universities at outstanding conditions. And yeah, private organizations, they pay a little bit more, but it's still, we believe it's very affordable. So please contact us for more details. I think now it's time for the Q&A. So your questions and our answers. So let's take a look what we have. So you can still put your questions. We will answer them. So let's take a look what we have. So I guess it's here. Yeah, it's here. So I will take a few of them and read them, and let's go. Let's take a look. Yeah. So the first one from Ahmed, he has left already, but it doesn't matter. Is the rotor and stator actually rotating in URAN's simulation? And also how to define frozen rotor instead of mixing plane interfaces. So Radek, may I ask you to answer this question? So I will switch to you, and yeah, it's your turn again.
Okay, back to live. So I will hide my this window. Okay. So yeah, well, so I will open my geometry. For example, the frozen rotor in general can be applied not for the segment cases or where the interface is not the same for for the rotor part and stator part. So I will get the full view. So I will just open to see the geometry and see the TCFD. Okay. So I will load it. Okay, all right, great. So in the simulation here we set a steady state case. So this is the runs. This is not the U runs. This is the runs of steady state simulation. So it means it's a steady state, nothing is rotating physically, there is the MRF approach applied to the rotor part. So it simulates, it just transforms the Navier-Stokes equation into the rotational framework. The same is for the Urans, which is which is this steady state plus transient, and means static mesh plus MRF. It means it is Urans that the solver is transient, but still the MRF is applied, and physically it's nothing is rotating. But if you use this real mesh motion with dynamic mesh, then it really is the dynamic mesh motion, real rotation is simulated, and using this approach we have generated the video you see at the beginning of this webinar. So this is this free option. So run simulation, run simulation, and really transient simulation using, for example, LES or again the runs turbulence modeling, or DES or something similar. And the second the question was the frozen rotor. Yeah, so the frozen rotor can be applied only when you have really the full correspondence between the rotor part and stator part. It cannot be applied to the segment part, because as you can see, this interface is not connected fully to this interface. So on this type of interfaces, this mixing plane approach should be defined, and the frozen rotor for this type, and it is defined simply here inside the components. Okay. Where is it? Oh, sorry, it's here. I hope components. Yeah, right here. And then right, large it. This is this number. So this number defines the number of mixing planes, and if I set the 0, it means there is no mixing plane, and the AMI approach is defined with this basically the freezing freeze rotor approach. Yeah, so you simply to set this number to 0 enables this freezing rotor approach. And was there any other question?
Yeah, I'll continue. So, yeah, is there a way to model turbulence transition? So it's a question on transition model to turbulence, from laminar to turbulence, right? So would you go for it, or
I can answer it. I don't know by heart the exact name of the turbulence model which OpenFOAM provides, but this model can be implemented or can be connected to TCFD. Simply using this scripting, we can create a script which changes the turbulence, or which can set any turbulence model which OpenFOAM provides. Yeah, so I don't remember it. It's not this V2F, but yeah.
I think it's KKL, right? Okay. Yeah. But anyway, let's go ahead. So yeah, the external meshes can be loaded from MSH, but we are short of time. We cannot show it right now. But yeah, for sure, of course, you can load MSH meshes of Fluent, for example, to TCFD. It's very easy. Yeah, you can contact us regarding this. Yeah, the next question: how can we make a good simulation of video of this fun? Yeah, perhaps I will. Yeah, someone is asking about this, about this video. It's a bit of playing around of in ParaView. It's no special software. It's just a playing around in ParaView. Of course, we have added a little of those texts and GNU plots, but it's only a matter of a little playing in ParaView. You can visualize surface, colored surface, or even a volume, and you can export multiple images and then make them run. So it's no special miracles. It's pretty it only takes a time to play around. So you can contact us and we can give you a hint on this. So it was this. Yeah, the part for CAD design of the turbo machine CFD is inside the software, and no, it is not. So the design has to come from somewhere else. The engineers or the users come with their design, and turbo machinery CFD is a simulation tool, right? So turbo machinery CFD is simulation tool for turbo machinery. The design has to come from another software. Yes. Next question. This live example is already downloadable. Yes, it can be downloaded on our website, so you can easily find it in the download section on our website, and in the download cases you can find this exact tutorial which you can use directly in the demo, for example. Yes, and the next question from Aditya, is it necessary to develop a complicated turbo volume, or we can use only the cylinder? I think the question means whether we need a periodic case. No, of course you don't. You can use the full wheel or a periodic blade, for example, or periodic stage. So this is clear. So I think it's this is it. I think this is it. So I think it's time to conclude. So which brings me to the end. So it's really it. So thank you for your attention. Stay tuned with us. You can contact us anytime. We will gladly support you. We will gladly answer all your questions. So feel free to contact us. Really, do not hesitate. We like communicating these problems. It's our job and also our pleasure. So I guess this is nearly it from me. I ask Radek, anything to say?
Yeah, I just want to say thank you all of you. Thank you for attention, and as Luboš already said, if you have any question or comment, we are here for you. We are really looking forward to help you and to cooperate with you to improve your CFD workflow. So do not hesitate to contact us with any question. We are here for you. So thank you for watching, and see you next time. Hear you next time. Bye bye.
So yeah.
Yeah. Okay. Yeah. So bye bye.
Bye bye. Have a nice day.
Yeah. This is really it.